Right now, at this very moment, as you sit there watching this video, something extraordinary is happening all around you. Something invisible, something silent, something so fundamentally strange that even the greatest physicists of the 20th century struggled to wrap their minds around it. You think the space around you is empty. You look at the gap between your hand and your screen, and you see nothing there. You look up at the night sky, at the vast dark stretches between the stars, and you think that is emptiness. You think that is the void. You think that is nothing. But what if I told you that you are wrong? What if I told you that every single point in that so-called empty space is buzzing, humming, vibrating with an energy so immense, so incomprehensibly vast, that if we could somehow tap into even a tiny fraction of it, we could power every city on Earth for billions of years? What if I told you that the emptiest vacuum in the universe, a region with no atoms, no light, no radiation, no particles of any kind, still contains energy? Not just a little energy, not just a trace, but a staggering, mind-breaking amount of energy that makes nuclear bombs look like birthday candles. What if I told you that scientists have already proven this? That this is not science fiction, not speculation, not a theory waiting for evidence, but a measured, confirmed, experimentally verified fact of nature? And what if I told you that this energy, this zero-point energy, is not just some obscure curiosity buried in physics textbooks, but is actually the key to understanding why the universe exists at all, why galaxies formed, why stars shine, why you and I are here having this conversation right now? That is what today's video is about, and I promise you, by the time we are done, the way you see reality will never be the same again. We are going to go deep today, really deep. We are going to start from the very beginning, from the ancient Greeks who first asked whether empty space could truly exist. And we are going to travel all the way to the cutting edge of modern physics, to quantum field theory, to the Casimir effect, to Hawking radiation, to the birth of the universe itself, to the mind-bending possibility that everything we see, every galaxy, every star, every atom in your body, emerged from the energy of nothing. We are going to explore what zero-point energy really is at its most fundamental level. We are going to understand why Heisenberg's uncertainty principle guarantees that space can never truly be empty. We are going to see how two metal plates in a laboratory, placed incredibly close together in a vacuum, experience a mysterious force pushing them together, a force that comes from nowhere, from the energy of empty space itself. We are going to ask whether we can harvest this energy, whether free energy from the vacuum is possible, and we are going to be completely honest about what science actually says about that question. We are going to connect zero-point energy to dark energy, to the expansion of the universe, to black holes, to the deepest unsolved mysteries in all of physics. And we are going to do it all in a way that makes sense, step by step, building each idea on the last, so that by the end, you will understand something that most people on this planet have never even heard of. So before we dive in, if you are someone who loves science, if you are someone who stays up at night wondering about the mysteries of the universe, if you are someone who wants to understand how reality actually works at its deepest level, then you are in exactly the right place. Hit that subscribe button right now. Turn on the bell notification, because on this channel, we do not do surface-level science. We go deep. We go all the way down the rabbit hole. And trust me, this particular rabbit hole goes deeper than you can possibly imagine. Also, I want to know where you are watching from right now. Drop your city and your country in the comments. Are you watching from Karachi? From Delhi? From London? From New York? From Lagos? From Jakarta? Wherever you are on this beautiful planet, let me know, because this is a global community of curious minds, and I want to see how far this video reaches. Now, let us begin at the beginning. And the beginning, as it often does in science, starts with a question that seems simple, but turns out to be anything but. The question is this: can space be truly empty? Can there be a region of the universe that contains absolutely nothing, no matter, no energy, no fields, no forces, nothing at all? Just pure, perfect void? This question is older than science itself. More than 2,000 years ago, the ancient Greek philosophers wrestled with it. On one side, you had thinkers like Democritus and his teacher Leucippus, who believed that the universe was made of tiny, indivisible particles called atoms, and that these atoms moved through empty space, through void. For Democritus, the void was real. It was the stage on which the drama of existence played out. Atoms danced through emptiness, colliding, combining, separating, and from their interactions, everything we see was built. On the other side, you had Aristotle, perhaps the most influential philosopher who ever lived, and Aristotle said no. Nature abhors a vacuum. There can be no such thing as truly empty space. Every region of the universe must be filled with something. If you remove the air from a container, something else would rush in to fill the gap. Emptiness, for Aristotle, was not just unlikely. It was impossible. It was a logical contradiction, and for nearly 2,000 years, Aristotle's view dominated Western thought. The idea that space could be truly empty was considered absurd, almost heretical. But then came the scientific revolution. In the 17th century, a brilliant Italian physicist named Evangelista Torricelli, a student of Galileo, performed a remarkable experiment. He took a long glass tube, sealed at one end, filled it with mercury, and inverted it into a dish of mercury. The mercury in the tube dropped down to a certain level, and above it, at the sealed top of the tube, there appeared to be a gap. A space with nothing in it. No air, no mercury, nothing. Torricelli had created what appeared to be a vacuum. This was a direct challenge to Aristotle's claim that nature abhors a vacuum. And shortly after, Blaise Pascal, the French mathematician and physicist, extended these experiments, even sending his brother-in-law up a mountain with a barometer to show that atmospheric pressure decreased with altitude, confirming that the space above the mercury truly was evacuated of air. But was it truly empty? That question lingered, because even if you removed all the air, even if you removed every atom and molecule from a region of space, you still had to contend with something else. You still had to contend with light. Light could pass through a vacuum. The sun's light reached Earth across millions of miles of apparently empty space. And in the 19th century, physicists became convinced that light, like sound, must travel through some medium. Sound needs air. Water waves need water. So light, they reasoned, must need something too. And they called this hypothetical something the luminiferous ether. The ether was supposed to fill all of space, providing the medium through which light waves propagated. It was supposed to be invisible, weightless, perfectly transparent, and yet rigid enough to support the incredibly high-frequency vibrations of light. It was, in many ways, A strange and uncomfortable idea, but it was the best explanation they had. And then came one of the most famous experiments in the history of science. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to detect the ether. Their reasoning was simple. If the Earth is moving through the ether as it orbits the sun, then light traveling in the direction of Earth's motion should move at a slightly different speed than light traveling perpendicular to it, just as a swimmer moves at different speeds when swimming with the current versus across the current. Michelson and Morley built an incredibly precise instrument called an interferometer, which could detect differences in the speed of light with extraordinary accuracy. They performed their experiment, and they found nothing, no difference. No matter which direction they measured, the speed of light was the same. The ether did not exist. Or if it did, it had no detectable effect whatsoever. This result shocked the physics world. It created a crisis. If there was no ether, what was light traveling through? How did electromagnetic waves propagate through empty space? And it was this crisis that led a young patent clerk in Bern, Switzerland, to propose something radical. His name was Albert Einstein, and in 1905, he published his special theory of relativity, which declared that light does not need a medium. Light is a self-propagating electromagnetic wave that travels through empty space at a constant speed, the same speed for all observers, regardless of their motion. There was no ether. Space really could be empty, or so it seemed, because here is where the story takes its first great twist. Just as Einstein was dismantling the ether and establishing that space could be truly empty, another revolution was brewing in physics, a revolution that would ultimately prove that space is anything but empty. And that revolution was quantum mechanics. The story of quantum mechanics begins in the year 1900 in the city of Berlin, with a physicist named Max Planck. Planck was trying to solve a specific problem, a problem that had been plaguing physicists for years. It was called the black body radiation problem. When you heat an object, it glows. A piece of iron heated to a few hundred degrees glows red. Heat it more, and it glows orange, then yellow, then white. The question was, how does the intensity of this radiation vary with its frequency? Classical physics, using the laws of thermodynamics and electromagnetism that were known at the time, made a prediction, and that prediction was catastrophically wrong. Classical physics predicted that a hot object should radiate infinite energy at high frequencies, a result so absurd that it was called the ultraviolet catastrophe. Clearly, something was deeply wrong with the existing physics. Planck found the solution, but it required him to make an assumption that he himself found deeply uncomfortable. He had to assume that energy is not continuous. Energy does not flow like water. Instead, energy comes in discrete packets, in tiny indivisible units that he called quanta. The energy of each quantum was proportional to the frequency of the radiation, connected by a new fundamental constant that we now call Planck's constant, denoted by the letter H. This was a revolutionary idea. It went against everything physicists believed about the nature of energy. Planck himself initially thought it was just a mathematical trick, a convenient assumption that happened to give the right answer. He did not realize that he had opened the door to an entirely new understanding of reality. But others walked through that door. In 1905, the same miraculous year in which he published Special Relativity, Einstein used Planck's quantum idea to explain the photoelectric effect, the observation that light shining on a metal surface can eject electrons. Einstein proposed that light itself comes in quanta, in discrete packets of energy that we now call photons. This was radical because it meant that light, which had been understood as a wave for over a century, also behaved as a particle. The quantum revolution had begun in earnest. Over the next 2 decades, quantum mechanics developed rapidly. Niels Bohr applied quantum ideas to the atom, proposing that electrons orbit the nucleus only at certain allowed energy levels, jumping between them by absorbing or emitting quanta of light. Louis de Broglie proposed that not just light, but all matter, all particles, have wave-like properties. Erwin Schrödinger developed a wave equation that described how these quantum waves evolve over time. And in 1927, Werner Heisenberg discovered something that would change everything, something that lies at the very heart of our story today. Heisenberg discovered the uncertainty principle, and this is where zero-point energy is born. The uncertainty principle is one of the most profound and counterintuitive ideas in all of science. It tells us that there are fundamental limits to what we can know about a physical system. Specifically, it tells us that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our measuring instruments. It is not that our tools are not good enough. It is a fundamental feature of nature itself. At the quantum level, reality is inherently fuzzy, inherently uncertain, inherently indeterminate. Now let me explain why this matters so much for our story. Think about what it means for something to be truly at rest, for something to have zero motion, zero energy. If a particle were perfectly at rest, we would know 2 things about it with perfect precision. We would know its position, because it is not moving, it is fixed in one place, and we would know its momentum, because its momentum is exactly zero. But the uncertainty principle says this is impossible. You cannot simultaneously know both the exact position and the exact momentum. If you know the momentum is exactly zero, the position becomes completely uncertain. The particle could be anywhere. And if you know the position exactly, the momentum becomes completely uncertain. The particle could be moving at any speed. This means that a particle can never be perfectly at rest. There must always be some residual motion, some minimum amount of jiggling, even at the lowest possible energy state. Even if you cool a system down to absolute zero, the coldest temperature theoretically possible, minus 273.15 degrees Celsius, where all thermal energy has been removed, there is still motion, still vibration, still energy. This residual, irreducible rock-bottom energy is what we call zero-point energy. It is the energy that remains when you have removed everything you possibly can. It is the energy of nothing, the energy of the ground state, the energy that the uncertainty principle absolutely demands must exist. Let me give you an analogy to make this more concrete. Imagine you have a ball on a hill. It rolls down to the bottom of a valley. In classical physics, at the very bottom of the valley, the ball would sit perfectly still. It would have zero kinetic energy. It would be at rest. But in quantum mechanics, the ball can never sit perfectly still at the bottom. The uncertainty principle says it must always be jiggling, always vibrating, always moving at least a little bit. The ball in the valley can reach its lowest possible energy state, but that state still has energy. It is not zero. That is 0-point energy. Now here is where it gets really interesting. This principle does not just apply to individual particles. It applies to fields. And in modern physics, fields are everything. Let me explain what I mean. In quantum field theory, which is the most fundamental framework we have for understanding the universe is not made of particles. Not really. The universe is made of fields. There is an electron field that permeates all of space. There is a photon field, an electromagnetic field that fills all of space. There are quark fields, gluon fields, neutrino fields, the Higgs field, and many others. Every type of particle corresponds to a field, and the particles themselves are just excitations of these fields. An electron is a vibration in the electron field. A photon is a vibration in the electromagnetic field. A quark is a vibration in the quark field. The particles are like waves on an ocean. The ocean is the field. The waves are the particles. Now, here is the crucial point. The uncertainty principle applies to these fields just as it applies to particles. Just as a particle can never be perfectly at rest, a field can never be perfectly calm. A field can never have exactly zero value everywhere. There must always be fluctuations, tiny random variations, quantum noise. Even in the vacuum, even when there are no particles at all, the fields are still fluctuating. They are still jiggling. They are still vibrating with that irreducible quantum minimum. These fluctuations are called quantum vacuum fluctuations. And the energy associated with them, the energy of these smallest possible vibrations of every quantum field at every point in space, is 0-point energy. Think about this for a moment. At every single point in space right now, even in the emptiest void between the galaxies, every quantum field is fluctuating. The electromagnetic field is fluctuating. The electron field is fluctuating. The quark fields are fluctuating. All of them, all at once, everywhere, all the time. And each of these fluctuations carries energy, 0-point energy, the energy of the vacuum. Space is not empty. It never was. It never can be. The uncertainty principle forbids it. The quantum nature of reality demands that even nothing is something. And that something is 0-point energy. If you could somehow look at the vacuum with quantum eyes, if you could zoom into the smallest scales and see what is really happening in empty space, you would not see nothing. You would see a seething, roiling, bubbling cauldron of activity, virtual particles appearing and disappearing, fields fluctuating wildly, energy popping in and out of existence. The vacuum is not a dead, inert void. It is the most energetic, the most dynamic, the most alive thing in the universe. And this is not poetry. This is not metaphor. This is physics. Measured, tested, confirmed physics. But before we get to the experimental proof, I want to make sure you understand something important about the history of this idea, because 0-point energy was not discovered overnight. It was not a single eureka moment. It was a gradual realization, built up over decades by many brilliant minds, and the story of its discovery is as fascinating as the concept itself. The first person to mathematically describe 0-point energy was, surprisingly, Albert Einstein. Yes, the same Einstein who dismantled the ether and established special relativity. In 1913, Einstein and his colleague Otto Stern published a paper analyzing the thermodynamic properties of a gas at low temperatures. In their analysis, they found that even at absolute zero, the molecules of the gas would retain a residual energy 1/2 h times nu for each degree of freedom, where h is Planck's constant and nu is the frequency of vibration. This was the first explicit calculation of zero-point energy. Einstein initially included it to get the right answer for specific heat calculations, and later, interestingly, he questioned whether it was real or just a mathematical artifact. But subsequent developments in quantum mechanics confirmed that it was absolutely real. The mathematical framework that made zero-point energy rigorous came with the development of quantum mechanics in the 1920s, when Heisenberg, Schrödinger, Dirac, and others developed the full mathematical machinery of quantum theory. The existence of zero-point energy fell out naturally from the equations. Consider the simplest possible quantum system, the quantum harmonic oscillator. This is just a particle attached to a spring, vibrating back and forth. In classical physics, you can make this particle perfectly still. You can drain all its energy to zero. But in quantum mechanics, when you solve the Schrödinger equation for this system, you find that the allowed energy levels are given by a beautiful, simple formula. The energy equals n plus 1/2, all multiplied by h bar times omega, where n is a whole number representing the energy level starting from zero, h bar is Planck's reduced constant, and omega is the natural frequency of the oscillator. The key here is the 1/2. Even when n equals 0, when the oscillator is in its ground state, its lowest possible energy level, the energy is not 0. It is 1/2 or h bar omega. That is the zero-point energy, and this result carries over directly to quantum field theory. Every mode of every quantum field, and there are infinitely many modes at every point in space, has a minimum energy of 1/2 h bar omega. And when you add up all these minimum energies across all modes, across all fields, across all of space, you get the total vacuum energy, the total zero-point energy of the universe. And this is where things get truly mind-bending, because when you actually do this calculation, when you actually add up all the zero-point energies of all the field modes, you get infinity. Literally infinity, an infinite amount of energy in every cubic centimeter of space. Now, obviously, space does not contain infinite energy. If it did, the gravitational effects would be catastrophic. The universe would either have collapsed into a singularity or expanded so rapidly that no structures could ever have formed. So something is clearly wrong with the naive calculation, and this is one of the deepest, most troubling, most fascinating unsolved problems in all of physics. We will come back to it later because it connects to dark energy and the fate of the universe. But for now, the important point is this: zero-point energy is real. The vacuum has energy. And even though we do not fully understand how to calculate its total amount, we have experimental proof that it exists. And that brings us to one of the most beautiful, most elegant, most convincing experiments in the history of physics. An experiment that proves, beyond any shadow of doubt, that empty space has energy. It is called the Casimir effect. The story begins in 1948 in the Netherlands at the Philips Research Laboratories in Eindhoven. A Dutch physicist named Hendrik Casimir was working on the theory of colloidal chemistry, studying the forces between tiny particles suspended in a fluid. In the course of this work, he and his colleague Dirk Polder discovered something unexpected. They found that the forces between neutral atoms, atoms with no net electric charge, were different from what classical physics predicted. Classical physics said these forces, called van der Waals forces, should decrease with distance according to a certain power law. But Casimir and Polder found that at large distances, the forces decreased faster than expected. And the reason, they realized, was that the vacuum fluctuations of the electromagnetic field, the zero-point energy, were modifying the forces between the atoms. This led Casimir to a brilliant insight. He realized that if vacuum fluctuations could affect atoms, they should also affect macroscopic objects. And he devised a thought experiment that has become one of the most famous in all of physics. Imagine, he said, two perfectly flat, perfectly smooth, uncharged metal plates placed very close together in a vacuum. Remove all the air, remove all the radiation, make the space between them and around them as empty as physically possible. Now, classical physics says nothing should happen. There is no charge, no magnetic field, no force of any kind to push or pull these plates. They should just sit there, inert and motionless. But Casimir predicted that the plates would be pushed together by an invisible force, a force coming from the vacuum itself, a force generated by zero-point energy. Here is why. The vacuum is filled with electromagnetic fluctuations, virtual photons popping in and out of existence at every possible wavelength. Outside the plates, all wavelengths are possible. The virtual photons can have any wavelength they like. But between the plates, the situation is different. Between the plates, only certain wavelengths fit. The wavelengths must be such that a whole number of half wavelengths fits between the plates, similar to the way a guitar string can only vibrate at certain frequencies, the fundamental and its harmonics. Any wavelength that does not fit between the plates is excluded. This means that between the plates there are fewer modes of vibration, fewer virtual photons, less zero-point energy. Outside the plates, there are more modes, more virtual photons, more zero-point energy. The energy density outside the plates is higher than the energy density between them. And this difference in energy density creates a pressure, a net force pushing the plates together. Let me give you an analogy. Imagine two large ships anchored side by side in a rough sea. Between the ships, the water is somewhat sheltered. Only certain wave patterns fit in the narrow gap. But outside the ships, the sea is fully rough with waves of all sizes. The rougher water outside pushes more strongly against the outer surfaces of the ships than the calmer water between them pushes against their inner surfaces. The result is that the ships are pushed together. This is essentially what happens in the Casimir effect. But instead of water waves, it is quantum vacuum fluctuations. And instead of ships, it is metal plates. Casimir calculated the exact force for two perfectly conducting, perfectly flat plates separated by a distance d. The force per unit area is given by pi squared times h bar times c, divided by 240 times d to the fourth power. This is an incredibly tiny force. For plates separated by 1 micrometer, 1/1,000,000th of a meter, the pressure is only about 1/100th of a pascal, roughly equivalent to the gravitational weight of a red blood cell spread over a square centimeter. But it is there, it is real, and it is a direct, measurable consequence of zero-point energy. Now, Casimir published his prediction in 1948. But measuring such a tiny force was extraordinarily challenging with the technology of that era. The first attempt at measurement came in 1958, when a Dutch physicist named Marcus Sparnay tried to verify the effect. His results were consistent with Casimir's prediction, but the experimental uncertainties were too large to be considered a definitive confirmation. The error bars were simply too big. For decades, the Casimir effect remained an interesting theoretical prediction without a precise experimental confirmation. But then, in 1997, a physicist named Steve Lemereau at the University of Washington performed a landmark experiment. Using a torsion pendulum and a gold-coated sphere near a flat plate, rather than two flat plates, which are much harder to align perfectly, Lemereau measured the Casimir force with an accuracy of about 5%. His results confirmed Casimir's prediction beautifully. The force was there, exactly as Casimir had predicted, exactly as quantum field theory demanded, and the measurements got even better. In 1998, Umar Mohideen and Anushree Roy at the University of California, Riverside used an atomic force microscope to measure the Casimir force between a gold-coated sphere and a flat plate with an accuracy of about 1%. Their results matched the theoretical prediction with stunning precision. Since then, numerous experiments around the world have confirmed the Casimir effect with ever-increasing accuracy. It is now one of the most well-established phenomena in all of quantum physics. Let me emphasize what this means. The Casimir effect is a direct, macroscopic, measurable, observable consequence of the zero-point energy of the vacuum. It proves that empty space has energy. It proves that the vacuum is not empty. It proves that the quantum fluctuations of the electromagnetic field are real and have physical effects. This is not speculation. This is not theory waiting for evidence. This is experimental fact. The energy of nothing has been measured, and it pushes things around. If you are finding this fascinating, and I hope you are, then do me a favor. Hit that like button right now. I know it seems like a small thing, but it makes a huge difference. When you like a video, the algorithm shows it to more people, and more curious minds get to learn about the incredible universe we live in. Also, drop a comment right now. I want to know, did you know before watching this video that empty space has energy? Did you know about zero-point energy? Write yes or no in the comments. I am genuinely curious to see how many people already knew about this. Now, the Casimir effect is the most famous proof of zero-point energy, but it is not the only one. There are other experimental confirmations, and some of them are even more precise and dramatic. Let me tell you about two of them. The first is called the Lamb shift. In 1947, just 1 year before Casimir published his prediction, an American physicist named Willis Lamb made a discovery that would earn him the Nobel Prize. Lamb was studying the energy levels of hydrogen, the simplest atom in the universe, just one proton and one electron. According to the Dirac equation, which is the relativistic quantum mechanical equation for the electron, two particular energy levels of hydrogen, called the 2s1/2 and 2p1/2 states, should have exactly the same energy. They should be perfectly degenerate, as physicists say, but Lamb, using precise microwave spectroscopy, found that they were not the same. The 2s1/2 level was slightly higher in energy than the 2p1/2 level by a tiny amount, about 1057 megahertz, a frequency so small that it had been missed by all previous measurements. This tiny energy difference became known as the Lamb shift. What causes it? The vacuum, zero-point energy. The fluctuations of the electromagnetic vacuum constantly jostle the electron as it orbits the proton. The virtual photons appearing and disappearing all around the electron give it a tiny, random, perpetual shaking. This shaking slightly changes the electron's average position, and because the 2s and 2p states have different spatial distributions, the vacuum fluctuations affect them differently, lifting the degeneracy and creating the Lamb shift. Now, here is what is truly extraordinary. Using quantum electrodynamics, which is the quantum field theory of the electromagnetic interaction, physicists can calculate the Lamb shift from first principles, including the effects of vacuum fluctuations, and the calculated value agrees with the measured value to an astonishing precision. We are talking about agreement to better than 1 part in a billion. This is one of the most precise predictions in all of science, and it is a direct consequence of zero-point energy. The second proof I want to tell you about is even more precise. It is the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet with a property called the magnetic moment. Dirac's equation predicts a specific value for this magnetic moment, characterized by a number called the G factor, which Dirac's theory virtual particles appearing and disappearing around the electron modify its magnetic properties. The electron is constantly emitting and reabsorbing virtual photons, and these virtual photons briefly fluctuate into virtual electron-positron pairs, and those pairs affect the electron's magnetic moment. When you calculate this using quantum electrodynamics, including contributions from vacuum fluctuations, the predicted value of the anomalous magnetic moment agrees with the measured value to more than 10 significant digits. Let me say that again. The theoretical prediction matches the experimental measurement to more than 10 decimal places. This is the most accurate prediction in the history of science. It is the greatest triumph of quantum field theory, and it is a direct consequence of the reality of zero-point energy and vacuum fluctuations. So let there be no doubt. Zero-point energy is real. The vacuum has energy. Space is not empty. This is not a philosophical claim. This is not a matter of interpretation. This is hard, experimental, measured, verified, confirmed, reproduced, indisputable fact. The Casimir effect, the Lamb shift, and the anomalous magnetic moment of the electron all prove it independently and with extraordinary precision. But this raises an enormous question. If the vacuum is full of energy, can we use it? Can we extract it? Can we tap into this vast ocean of quantum energy and power, our civilization? This is one of the most exciting, most controversial, and most misunderstood questions in all of physics. And to answer it properly, we need to think very carefully about what zero-point energy actually is and how the laws of physics constrain what we can and cannot do with it. Let us start with the dream. The dream of zero-point energy extraction is simple and enormously seductive. Zero-point energy is everywhere. It fills all of space. It is not localized in some particular place that you need to travel to. It is not dependent on the weather, like solar energy. It is not dependent on geography, like hydroelectric power. It is not a finite resource that can be depleted, like fossil fuels. It does not produce waste, like nuclear fission. In principle, it is the ultimate energy source, ubiquitous, limitless, clean, and eternal. If we could somehow extract even a tiny fraction of the zero-point energy contained in a single cubic meter of empty space, we would have enough to run the entire Earth for years. If we could build a zero-point energy engine, we would never need any other energy source again. We could power starships. We could solve the climate crisis. We could lift every person on Earth out of energy poverty. The implications would be beyond transformative. They would be civilization-altering. This dream has captured the imagination of science fiction writers for decades. In the television series Stargate Atlantis, the ancient hyper-advanced civilization of the ancients powered their technology with ZPMs, zero-point modules, devices that extracted energy from subspace, essentially from the quantum vacuum. In the Marvel Cinematic Universe, the quantum realm, with its strange energy properties, has been a plot device in several films. In numerous video games and novels, zero-point energy is the standard power source of advanced civilizations. It has become a trope of science fiction, a shorthand for technology so advanced that it has transcended all the limitations we currently face. But science fiction is one thing, and science fact is another. The question is not whether zero-point energy exists. We have already established that it does. The question is whether we can extract it. And this is where things get complicated. Very complicated. The fundamental problem is this. Zero-point energy is the ground state energy. It is the lowest possible energy state of a quantum system. And in thermodynamics, you can only extract energy from a system by moving it to a lower energy state. This is a fundamental principle of physics. Think about it this way. You can get energy from water by letting it fall from a height to a lower height. The water flows downhill, and you capture the energy of its motion with a turbine. But what if the water is already at sea level? What if there is nowhere lower for it to go? Then you cannot extract any energy from it. It is already at the bottom. Zero-point energy is analogous to the water at sea level. It is the lowest possible energy. There is, in principle, nowhere lower to go. You cannot extract energy from the ground state because there is no lower state to transition to. This is not just an engineering challenge. It is not just a matter of building better technology. It is a fundamental constraint imposed by the laws of quantum mechanics and thermodynamics. You cannot extract energy from a system that is already in its lowest energy state. Period. Or can you? This is where the story gets really interesting. Because while the basic argument against zero-point energy extraction is compelling, there are subtleties, loopholes, nuances, and legitimate scientific debates that make the situation much more complex than a simple yes or no. The first loophole involves the Casimir effect. We have already seen that the Casimir effect creates a measurable force between two metal plates. This force can, in principle, do work. If the plates move together under the Casimir force, they gain kinetic energy. That energy came from somewhere, and the only source is the vacuum, the zero-point energy of the electromagnetic field between and around the plates. So in some sense, the Casimir effect is already an example of extracting energy from the vacuum. In 1984, a physicist named Robert Forward, who worked at Hughes Research Laboratories and was also a prolific science fiction writer, proposed what he called a vacuum fluctuation battery. The idea was to use the Casimir effect to extract energy from the vacuum. You bring two plates close together, the Casimir force pushes them together and does work, and you capture that energy. It is a beautifully simple concept. But there is a catch. Once the plates are in contact, to extract more energy, you need to pull them apart again. And pulling them apart requires at least as much energy as you gain from them coming together. It is like a spring. You can release the energy stored in a compressed spring, but to recompress it, you need to put that energy back in. The net energy gain is 0 or less. Forward and others have explored more sophisticated schemes involving cycles of plate separation changes in the material properties of the plates, and other clever tricks. But the consensus among most physicists is that while you can cycle energy through the Casimir effect, you cannot extract net energy from the vacuum using this method. The vacuum is like a reservoir that you can interact with, that you can exchange energy with, but that you cannot drain. However, there is a second, much more dramatic loophole, and it has actually been demonstrated in the laboratory. It is called the dynamical Casimir effect. The regular Casimir effect involves static plates. The dynamical Casimir effect involves moving boundaries. The prediction, first made by Gerald Moore in 1970 and elaborated by many others, is this: if you move a mirror, a reflective surface, fast enough, you can literally create real photons out of the vacuum. Not virtual photons. Real, detectable, observable photons. Light from nothing. The mechanism is related to the regular Casimir effect. The vacuum fluctuations near the mirror are constantly trying to produce virtual photons that appear and disappear, but if the mirror is accelerating, it can interact with these virtual photons and promote them to real photons. The energy for these photons comes from the kinetic energy of the mirror, but the mechanism of their creation is purely quantum, a direct interaction between a moving boundary and the vacuum fluctuations. The problem is that to create a significant number of photons, you need to move the mirror at a speed comparable to the speed of light, and no physical mirror can be moved that fast. So for decades, the dynamical Casimir effect remained a theoretical prediction. But in 2011, a team of physicists at Chalmers University of Technology in Sweden found a brilliant workaround. Instead of moving a physical mirror, they used a superconducting quantum interference device, a SQUID, to rapidly change the electrical boundary conditions of a superconducting circuit. Effectively, they created a mirror whose position oscillated at about 5% of the speed of light, not by physically moving anything, but by changing the electromagnetic properties of the system at incredible speed, billions of times per second. And it worked. They detected real photons emerging from the vacuum, real particles of light, created from nothing from the quantum vacuum by the dynamical Casimir effect. This is an extraordinary result. It demonstrates that the vacuum really can be a source of real particles. The photons that emerged were not already there. They were created by the interaction between the moving boundary and the vacuum fluctuations. In a very real sense, something came from nothing. But does this mean free energy? No. The energy of the photons came from the energy used to drive the SQUID, to oscillate the boundary conditions. The system did not produce more energy than was put in. It was not free energy. It was a conversion of mechanical or electrical energy into photons via the vacuum. Fascinating physics, but not a perpetual motion machine. There is a third avenue of research that I want to mention because it is more speculative but deeply interesting. It involves a framework called stochastic electrodynamics, or SED. Standard quantum mechanics treats the vacuum fluctuations as inherently quantum, as features of the quantum ground state that cannot be reduced or extracted. But SED takes a different approach. It models the zero-point field as a real classical electromagnetic field that fills all of space and is the source of quantum behavior. In this view, the uncertainty principle, quantum tunneling, atomic stability, and other quantum phenomena are not fundamental features of reality, but are instead caused by the constant interaction of matter with this background zero-point radiation. Physicists like Harold Puthoff and Bernhard Heisch have explored whether, within the SED framework, it might be possible to extract energy from the zero-point field. They argue that since in their framework the zero-point field is a real field with real energy, it should in principle be possible to interact with it and extract energy, just as you can extract energy from any other electromagnetic field. They have published papers proposing specific mechanisms, including one involving interactions between the zero-point field and matter at the quantum level that could lead to asymmetric forces. However, it is important to be honest about the status of this research. SED is not mainstream. It is a minority view. Most physicists do not accept it as a valid alternative to standard quantum mechanics, and there are significant theoretical problems with the SED approach. The mainstream consensus remains that while zero-point energy is real, it cannot be extracted in a way that violates thermodynamics. But the SED researchers would argue that the last word has not been spoken and that our understanding of the vacuum is still incomplete. There is also the matter of government interest in zero-point energy research, and this is where things get a little bit cloak and dagger. Various government agencies, including NASA and DARPA, the Defense Advanced Research Projects Agency of the United States, have funded research into zero-point energy and its potential applications. At NASA, a physicist named Harold White, who led the EagleWorks laboratory at the Johnson Space Center, investigated several advanced propulsion concepts, including the quantum vacuum plasma thruster, a device that was claimed to interact with the quantum vacuum to produce thrust without conventional propellant. White also worked on the M-Drive, a controversial device that appeared to produce thrust without expelling any mass, in apparent violation of Newton's third law. While the M-Drive results were widely criticized and could not be independently reproduced, the quantum vacuum plasma thruster concept was motivated by the idea that the vacuum fluctuations might be manipulable for propulsion. Perhaps even more intriguing are the so-called PIES patents. Between 2016 and 2019, a Navy scientist named Salvatore Cesar Pies filed several patents on behalf of the United States Navy for exotic technologies, including a high-energy electromagnetic field generator that was claimed to have connections to zero-point energy manipulation. The patents describe devices of almost science-fictional capability, including room temperature superconductors, inertial mass reduction devices, and compact fusion reactors. The Navy confirmed that the patents were real and that the Navy had a strategic interest in the technologies described. However, No working devices have ever been publicly demonstrated, and many physicists consider the patents to be speculative at best and pseudoscientific at worst. Why would governments be interested in zero-point energy? The answer is simple. The strategic implications are enormous. If zero-point energy extraction were even remotely possible, the nation that achieved it first would have access to unlimited energy. This would transform military capability, economic power, and geopolitical influence beyond recognition. Even if the probability of success is very low, the potential payoff is so vast that it justifies at least some investment in exploratory research. This is the logic of high-risk, high-reward research, and it explains why agencies like DARPA are willing to fund speculative projects that most mainstream scientists consider unlikely to succeed. So, where does the science actually stand on zero-point energy extraction? Let me give you the most honest, balanced assessment I can. The mainstream view, held by the vast majority of physicists, is that zero-point energy is real but cannot be extracted as a net source of usable energy. The ground state is the lowest energy state, and you cannot go lower. The Casimir effect demonstrates the reality of vacuum energy, and the dynamical Casimir effect shows that real particles can be created from the vacuum, but neither provides a mechanism for net energy extraction. The second law of thermodynamics holds, and perpetual motion machines remain impossible. However, it is also true that our understanding of the vacuum is incomplete. The vacuum catastrophe, the mismatch between the predicted and observed values of vacuum energy, tells us that something deep is wrong with our current theories. We do not have a quantum theory of gravity. We do not fully understand how vacuum energy gravitates. We do not know why the cosmological constant has the value it does. In the face of these profound gaps in our understanding, it would be arrogant to claim that we know for certain what is and is not possible. History teaches us that today's impossibility is sometimes tomorrow's technology. The very idea that atoms could be split for energy was once considered absurd. The very idea that the electromagnetic field could be used for communication was once considered fantasy. So the honest answer is this: we do not know for certain whether zero-point energy can be extracted. The best current understanding says no, but the best current understanding is also incomplete. And that is what makes this field so exciting. It is one of the great open questions at the frontier of physics, and the answer, whichever way it goes, will be profoundly important. Now, I want to take you on the next leg of our journey. We have understood what zero-point energy is. We have seen the experimental proof. We have explored the question of energy extraction. Now it is time to go even deeper. It is time to connect zero-point energy to the biggest, most cosmic, most awe-inspiring phenomena in the universe. Because zero-point energy is not just about metal plates and laboratory experiments. It is about the fabric of space-time itself. It is about the birth of the universe. It is about the ultimate fate of everything. And that starts with one of the most profound questions in physics. Does the vacuum weigh anything? According to Einstein's general theory of relativity, energy and mass are equivalent. This is the famous E equals mc squared. And if energy and mass are equivalent, then energy gravitates, energy curves space-time, energy has weight. So if the vacuum has energy, if every point in space contains zero-point energy, then the vacuum should have weight. The vacuum should curve space-time. The vacuum should have gravitational effects. This is an astonishing idea. It means that empty space itself, the nothing between the stars, is gravitating. It is pulling on things, or pushing on things. And this brings us to one of the greatest discoveries in the history of astronomy. A discovery that shocked the scientific world and won its discoverers the Nobel Prize. The discovery of dark energy. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other led by Brian Schmidt and Adam Rees, were studying distant supernovae, exploding stars that serve as cosmic distance markers. They were trying to measure the rate at which the expansion of the universe is slowing down. Because the universe has been expanding since the Big Bang, and gravity has been pulling everything back together, the expansion should be decelerating. The question was, how fast? What they found was the opposite of what anyone expected. The expansion of the universe is not decelerating. It is accelerating. The universe is expanding faster and faster over time. Something is pushing space apart, counteracting gravity, and causing the expansion to speed up. This something was given the name dark energy, and it constitutes approximately 68% of the total energy content of the universe. It is the dominant component of the cosmos, more than all the stars, all the galaxies, all the gas and dust and planets and people combined. Dark energy is the majority shareholder of the universe. And here is the connection to our story. The leading theoretical explanation for dark energy is that it is the energy of the vacuum. It is zero-point energy. The idea is simple and elegant. If empty space has energy, and if that energy has a constant density throughout the universe, then as the universe expands and more space is created, more vacuum energy appears. This creates a kind of cosmic repulsion, a pressure that pushes space apart and causes the expansion to accelerate. This is exactly what a cosmological constant in Einstein's equations would do. And the cosmological constant is exactly the term that represents vacuum energy. Einstein actually introduced the cosmological constant into his equations of general relativity back in 1917, long before the discovery of dark energy. He added it for a different reason, to keep the universe static, which was what he believed at the time. When Edwin Hubble discovered that the universe was expanding, Einstein removed the cosmological constant and reportedly called it his biggest blunder. But now it appears that a cosmological constant of vacuum energy is exactly what we need to explain dark energy. Einstein's blunder may have been one of his greatest insights. But here is where the story takes its most troubling turn. The cosmological constant problem, the vacuum catastrophe, the worst prediction in the history of physics. When quantum field theorists calculate the energy density of the vacuum using the standard methods of quantum field theory, adding up the zero-point energies of all the field modes up to some reasonable energy cutoff, they get an enormous number. Typically, the calculation gives a vacuum energy density of about 10 to the power of 113 joules per cubic meter. This is an incomprehensibly vast amount of energy. It is the density of a universe so dominated by vacuum energy that it would expand at a rate so fast that no galaxies, no stars, no atoms, nothing could ever form. When cosmologists measure the actual energy density of the dark energy from astronomical observations, they get a number that is vastly, absurdly, ridiculously smaller. The measured dark energy density is about 6 times 10 to the power of minus 10 joules per cubic meter. Compare the two numbers. The prediction, 10 to the 113. The measurement, 10 to the minus 10. The discrepancy is a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is, by any measure, the worst prediction in the history of science. It is not even close to being the worst prediction. It is in a class by itself. Nothing in the history of physics has ever been this wrong. Let me give you a sense of how absurd this discrepancy is. Imagine you are trying to predict the distance from your house to the nearest grocery store, and your prediction is off by a factor of 10 to the 120. That is not like saying the store is a mile away when it is really 10 miles away. That is not like saying the store is on the moon when it is really down the street. That is like saying the store is 10 to the 120 meters away, a distance so vast that it dwarfs the observable universe by a factor of 10 to the 90 or so. It is wrong on a scale that defies comprehension. This is the cosmological constant problem. And it is not just an embarrassment for theoretical physics. It is a deep, fundamental clue that something profound is missing from our understanding of the vacuum and its energy. We clearly do not understand zero-point energy as well as we think we do. Either our calculation of vacuum energy is wrong, or our understanding of how vacuum energy gravitates is wrong, or something else entirely is going on. Many approaches have been proposed to solve this problem, and none have fully succeeded. One approach involves supersymmetry, a hypothetical symmetry between bosons and fermions. In a supersymmetric universe, the vacuum energy contributions from bosonic fields and fermionic fields would exactly cancel each other, giving zero vacuum energy. This would solve the cosmological constant problem. But we know that supersymmetry, if it exists, must be broken, because we do not observe the supersymmetric partner particles that the theory predicts. And when supersymmetry is broken, the cancellation is not exact, and you end up with a vacuum energy that is still far too large, though somewhat smaller than the original calculation. The Large Hadron Collider at CERN has searched extensively for supersymmetric particles and has not found them, which is a significant blow to this approach. Another approach involves the anthropic principle and the multiverse. The idea is that the cosmological constant varies from one region of the universe to another, or from one universe to another in a multiverse scenario. In most regions, the cosmological constant is either too large and positive, causing the universe to expand too fast for structures to form, or too large and negative, causing the universe to collapse. Only in the rare regions where the cosmological constant happens to be very small can galaxies, stars, planets, and observers like us exist. We find ourselves in such a region not because there is a fundamental reason for the small value, but simply because we could not exist anywhere else. This is called the anthropic selection effect. Some physicists, including Steven Weinberg, who actually predicted the approximate value of the cosmological constant using anthropic reasoning before it was measured, find this approach compelling. Others find it deeply unsatisfying because it does not actually explain anything. It just says we are lucky. Other approaches include modifications of general relativity, dynamical dark energy models like quintessence, where the vacuum energy is not a constant but changes over time, emergent gravity theories like Eric Verlinde's proposal that gravity is not a fundamental force, but emerges from quantum information and various quantum gravity proposals. None of these have been conclusively confirmed or refuted. The cosmological constant problem remains one of the deepest unsolved mysteries in physics, and its solution will almost certainly require a revolutionary new understanding of the vacuum and its energy. Let me now take you even deeper into the nature of empty space. Because the story of zero-point energy is not just about the energy itself. It is about the fundamental nature of space-time, the fabric of the universe, and what happens to that fabric at the very smallest scales. In the 1950s, the great American physicist John Archibald Wheeler, who was a pioneer of general relativity and who gave black holes their name, proposed a remarkable idea. He called it quantum foam. Wheeler reasoned as follows. We know that the uncertainty principle causes quantum fluctuations in all fields, including the gravitational field. At everyday scales, these fluctuations are unimaginably tiny and smooth. Space appears flat and calm, like the surface of a lake seen from an airplane. But as you zoom in to smaller and smaller scales, the fluctuations become more and more violent, just as the lake surface, which looks smooth from a plane, reveals waves when you get closer, and turbulent molecular motion when you get closer still. Wheeler argued that at the very smallest scale in physics, the Planck scale, which is approximately 10 to the minus 35 meters, the quantum fluctuations of the gravitational field become so intense that the very geometry of spacetime breaks down. At this scale, space is not smooth. It is not flat. It is a writhing, bubbling, seething foam of constantly changing geometry. Tiny wormholes appear and disappear. The topology of space-time fluctuates wildly. The dimensionality of space itself may become ill-defined. Wheeler called this quantum foam, and it is driven by the zero-point energy of the gravitational field. We cannot directly observe quantum foam, at least not with any technology currently available. The Planck scale is far, far smaller than anything we can probe with our most powerful particle accelerators. But the concept has profound implications. It suggests that space-time itself, the arena in which all of physics plays out, is not a fixed, smooth stage, but a dynamic quantum entity that fluctuates and shifts at the smallest scales. It suggests that at the deepest level, there is no such thing as a smooth vacuum. The vacuum is wild, turbulent, and alive with quantum geometry. And this brings us to another mind-bending phenomenon connected to zero-point energy, the Unruh effect. In 1976, a Canadian physicist named William Unruh made a remarkable prediction based on quantum field theory in curved or accelerating reference frames. The Unruh effect says this: an observer who is accelerating through empty space will perceive the vacuum not as empty, but as filled with a bath of thermal radiation, a gas of warm particles. The temperature of this radiation is proportional to the acceleration. For an observer at rest, the vacuum is the vacuum, the cold, quiet ground state of the quantum fields. But for an observer who is accelerating, that same vacuum looks hot. It is full of real detectable particles. This is profoundly strange. It means that the concept of emptiness, the concept of the vacuum, is not absolute. It depends on the observer. What is empty for one observer is full of particles for another. The vacuum is relative. The temperature predicted by the Unruh effect is incredibly small for any realistic acceleration. You would need an acceleration of about 10 to the 20 meters per second squared roughly a billion times the acceleration due to gravity on Earth, to see a temperature of just 1 degree Kelvin. So the Unruh effect has never been directly observed, but it is firmly grounded in the same quantum field theory that gives us the Casimir effect and the Lamb shift, and most physicists are confident it is real. The Unruh effect is closely related to one of the most famous predictions in all of physics, a prediction that connects zero-point energy to black holes, to information, to the very deepest questions about the nature of reality. I'm talking about Hawking radiation. In 1974, Stephen Hawking, working at Cambridge University, made a prediction that stunned the physics world. He showed that black holes are not truly black. They radiate. They emit particles and slowly evaporate. How does this work? The explanation most commonly given involves vacuum fluctuations, zero-point energy. Here is the picture. In the vacuum near a black hole's event horizon, the boundary beyond which nothing can escape, virtual particle-antiparticle pairs are constantly being created and annihilated, just as they are everywhere in space. But at the event horizon, something special happens. Sometimes one particle of the pair falls into the black hole, and the other escapes to infinity. The particle that escapes is Hawking radiation. It carries positive energy away from the black hole. The particle that falls in can be thought of as carrying negative energy into the black hole, reducing its mass. Over time, the black hole loses mass and shrinks. Eventually, if it is not replenished by infalling matter, it evaporates completely. This is an extraordinary process. It means that black holes, the most extreme gravitational objects in the universe, the objects from which classically nothing can escape, are actually slowly leaking. And the leaking is powered by zero-point energy, by the vacuum fluctuations at the event horizon. The nothing of space is literally pulling the black hole apart, one particle at a time. Now, I should be honest and say that the virtual particle pair picture, while vivid and widely used, is somewhat simplified. The full derivation of Hawking radiation is much more subtle and involves the detailed behavior of quantum fields in curved space-time. The virtual particle picture captures the essence of the process, but glosses over many technical details. Hawking's original calculation was based on the behavior of quantum field modes propagating through the space-time geometry of a collapsing star, and the radiation arises from the mixing of positive and negative frequency modes at the horizon. But the key point remains: the vacuum, the zero-point energy, is essential to the process. Hawking radiation has never been directly observed from an astrophysical black hole. The temperature of the radiation is inversely proportional to the mass of the black hole. So for stellar mass black holes, the Hawking temperature is far below the temperature of the cosmic microwave background, making it impossible to detect with current technology. For the supermassive black holes at the centers of galaxies, the temperature is even lower. Only tiny black holes with masses comparable to a mountain would radiate at detectable temperatures, and no such black holes are known to exist. However, the physics of Hawking radiation has been confirmed indirectly through analog experiments. In 2016 and again in 2019, Jeff Steinhauer at the Technion in Israel created a sonic analog of a black hole using a Bose-Einstein condensate, a state of matter cooled to near absolute zero. In his experiment, sound waves played the role of light, and a region where the condensate flowed faster than the speed of sound created an acoustic event horizon. Steinhauer observed the emission of correlated pairs of sound quanta from this acoustic horizon, exactly as Hawking's theory predicts for real black holes. While this is not a direct observation of Hawking radiation from a gravitational black hole, it confirms the underlying quantum mechanism and gives physicists great confidence that Hawking's prediction is correct. Hawking radiation has profound implications. It suggests that black holes have a temperature and an entropy. It connects gravity, quantum mechanics, and thermodynamics in a deep and unexpected way. It leads to the black hole information paradox, one of the most debated problems in theoretical physics, which asks what happens to the information that falls into a black hole when the black hole evaporates. And it all traces back to zero-point energy, to the irrepressible quantum activity of the vacuum. Now, I want to take a step back and connect all of this to something even more grand, something that touches the very origin of existence, because zero-point energy is not just relevant to black holes and metal plates and electrons. It is relevant to the origin of the universe itself, the birth of everything. And this might be the most mind-blowing part of our entire journey. If you are still with me at this point, if you have followed along this far, then you are part of a special group. You are someone who genuinely wants to understand the deep workings of the universe. And I want to build this community of deep thinkers. So here is what I want you to do. Subscribe to this channel right now. Turn on all notifications so you never miss a video. And share this video with someone you know who loves science, someone who would appreciate going this deep. When you share knowledge, you multiply it. And leave a comment telling me which country you are watching from. I want to see how global this community is. Now, let us talk about the birth of the universe. The standard model of cosmology tells us that the universe began approximately 13.8 billion years ago in an event we call the Big Bang. But the Big Bang is widely misunderstood. Most people imagine it as an explosion, a point in space that suddenly detonated and sent matter flying outward in all directions. But that is not what happened. The Big Bang was not an explosion in space. It was an expansion of space itself. Space itself stretched, carrying matter and energy with it. There was no center of the explosion, no edge, no pre-existing space into which the universe expanded. Space itself was born, and it has been expanding ever since. But the very earliest moments of the Big Bang, the first tiny fractions of a second, are where things get really interesting. Because according to our best current theory, the very first thing that happened after the Big Bang, or possibly the thing that triggered the Big Bang itself, was a period of incredibly rapid expansion called cosmic inflation. Inflation was proposed in 1980 by Alan Guth, a physicist at MIT. The idea was motivated by several puzzles about the universe that the standard Big Bang model could not explain. Why is the universe so homogeneous, so uniform in temperature and density in all directions? Why is the geometry of space so flat, so close to Euclidean? Why do we not see certain exotic particles like magnetic monopoles that theories of high-energy physics predict should have been produced in the early universe? Guth proposed that all these puzzles could be solved if the universe underwent a brief period of exponential expansion very early in its history, expanding by a factor of at least 10 to the 26, and possibly much more, in a time interval of about 10 to the minus 36 to 10 to the minus 32 seconds. What drove this incredible expansion? Energy, specifically the vacuum energy of a quantum field. Guth proposed that in the very early universe, there existed a quantum field, which we now call the inflaton field, that was stuck in a high-energy state, a false vacuum. This false vacuum had an enormous energy density, much like a cosmological constant, but much larger. And this vacuum energy drove the exponential expansion of space. Eventually, the inflaton field decayed from its high-energy false vacuum state to its true vacuum state, releasing its energy in the form of particles and radiation. This is what we observe as the Big Bang. The hot, dense, particle-filled universe that emerged from inflation was born from the decay of vacuum energy. So in a very real sense, the Big Bang was powered by vacuum energy. The origin of the universe is intimately connected to zero-point energy and the quantum properties of the vacuum. But here is where it gets even more amazing. During inflation, the vacuum fluctuations of the inflaton field, the tiny random quantum jitterings of the field that are guaranteed by the uncertainty principle, played a cosmic role. These fluctuations were incredibly tiny, occurring at the subatomic level, but inflation stretched them. The exponential expansion of space took these microscopic quantum fluctuations and expanded them to cosmic scales, stretching them across the entire universe. When inflation ended and the universe settled down into its normal, slower expansion, these stretched quantum fluctuations became density variations, regions of slightly higher and slightly lower density in the primordial plasma. And these density variations, these seeds, grew over billions of years through the action of gravity into everything we see in the universe today. The galaxies, the galaxy clusters, the great cosmic web of filaments and voids, all of it. Every structure in the observable universe, from the largest supercluster to the smallest dwarf galaxy, grew from quantum vacuum fluctuations during inflation. Let me say that again, because it is one of the most profound statements in all of science. You exist because of quantum vacuum fluctuations. The atoms in your body, which were forged in stars that formed in galaxies that grew from primordial density variations, in variations that originated as quantum fluctuations of the vacuum during inflation. The chain of causation runs from the zero-point jiggling of a quantum field 13.8 billion years ago, through inflation, through the formation of structure, through stellar nucleosynthesis, through the formation of the solar system, through the evolution of life on Earth, all the way to you, sitting here watching this video. You are a child of the vacuum. You are a manifestation of zero-point energy, and we have direct observational evidence for this. The cosmic microwave background, the CMB, is the afterglow of the Big Bang, the oldest light in the universe. Released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This light has been traveling through the universe for over 13 billion years and now bathes us from every direction as a faint microwave glow. And when we map the CMB with exquisite precision, as the COBE satellite did in 1992, and the WMAP satellite did in the 2000s, and the Planck satellite did in the 2010s, we see tiny variations in temperature, tiny hot and cold spots, at a level of about 1 part in 100,000. These temperature variations are the imprint of the primordial quantum fluctuations. They are the cosmic fossils of zero-point energy. And when we compare the observed pattern of these variations with the predictions of inflationary theory, the predictions of quantum vacuum fluctuations stretched to cosmic scales, the agreement is spectacular. The theoretical predictions match the observations with remarkable precision across a wide range of angular scales. This is one of the great triumphs of modern cosmology, and it confirms, in the most dramatic way possible, that quantum vacuum fluctuations are not just an abstract theoretical concept, but are the origin of all structure in the observable universe. This connection between zero-point energy and the birth of the universe leads to an even more profound and philosophical question. Could the universe itself have emerged from nothing? Could the vacuum, the quantum void, have given birth to everything? This idea has been explored by several physicists, most notably Alexander Vilenkin and Lawrence Krauss. Vilenkin, in the 1980s, proposed a model in which the universe tunneled into existence from a state of literally nothing. No space, no time, no matter, no energy, nothing, through a quantum mechanical process called quantum tunneling. In quantum mechanics, particles can tunnel through energy barriers that they classically should not be able to cross. Vilenkin proposed that the universe itself tunneled from nothing into a tiny inflating bubble of space-time, which then grew into the vast cosmos we inhabit. Krauss, in his 2012 book, A Universe from Nothing, popularized a related idea. He argued that the total energy of the universe might be exactly zero. The positive energy of matter and radiation is exactly balanced by the negative energy of gravity. And if the total energy is zero, then creating the universe does not require any energy at all. The universe could have spontaneously appeared from a quantum fluctuation of the vacuum, a fluctuation that, because the total energy is zero, costs nothing and violates no conservation laws. These ideas are beautiful and provocative, but they are also controversial. Critics point out that nothing in these proposals is not truly nothing. Vilenkin's nothing still has the laws of physics, quantum mechanics, the potential for space-time to exist. Krauss's nothing still has quantum fields and vacuum energy. True philosophical nothing, the complete absence of everything, including the laws of physics themselves, is a much more radical concept, and it is not clear that physics can address it. But the debate itself illustrates the profound role that zero-point energy plays in our understanding of existence. The vacuum, the supposed void, may be the womb of the universe. The energy of nothing may be the source of everything, and if quantum vacuum fluctuations can create one universe, can they create others? This leads us to the concept of eternal inflation and the multiverse. The theory of eternal inflation, developed by Vilenkin, Andre Linde, and others, proposes that inflation, once it starts, never completely ends. In most of space, the inflating field decays to its true vacuum state and inflation stops, creating a region like our observable universe. But in other regions, quantum fluctuations push the inflating field back up to high-energy states, and inflation continues. These regions expand exponentially, and within them, further fluctuations create new bubbles of non-inflating space, each of which becomes a separate universe. The result is an ever-expanding, ever-reproducing multiverse, an infinite collection of universe bubbles, each with its own Big Bang, its own history, potentially its own laws of physics. Inflation never stops. New universes are born continuously, an endless process of cosmic creation driven by quantum vacuum fluctuations. This is an extraordinary and mind-stretching idea. If it is true, our observable universe is just one tiny bubble in an infinite ocean of bubbles. There may be universes where the laws of physics are different, where particles have different masses, where forces have different strengths. Some of these universes may be hospitable to life. Others may be completely sterile. The multiverse is the ultimate expression of the creative power of the vacuum. However, it is important to say that the multiverse remains highly speculative. It is a prediction of certain models of inflation, but it is not clear whether it can ever be observationally tested. If other universe bubbles are forever beyond our cosmic horizon, we may never be able to confirm or refute their existence. This makes the multiverse a scientifically contentious idea, more a prediction of our theories than an empirically established fact. But regardless of whether the multiverse exists, the connection between zero-point energy and the birth of the universe is firmly established. The vacuum energy of the inflating field drove inflation. The quantum fluctuations of the vacuum seeded the formation of all structure, and the energy of the vacuum may have given birth to the universe itself. Zero-point energy is not just a curiosity of quantum mechanics, it is the engine of creation. Now, I want to take you to some of the most advanced and cutting-edge aspects of zero-point energy physics. These are topics that push the boundaries of what we know and hint at the revolutions that may be coming. And the first of these is the Schwinger effect. Julian Schwinger was one of the greatest physicists of the 20th century, a contemporary of Richard Feynman and Freeman Dyson, and one of the founders of quantum electrodynamics. In 1951, Schwinger made a prediction that is, in its way, even more dramatic than the Casimir effect. He predicted that if you apply a sufficiently strong electric field to the vacuum, you can literally tear virtual particle-antiparticle pairs apart. Normally, virtual electron-positron pairs appear and disappear so quickly that they have no lasting effect. But if the electric field is strong enough, it can supply enough energy to the virtual pair to promote them to real permanent particles. The vacuum literally breaks down, and matter is created from nothing. Well, not from nothing. From the vacuum plus the energy of the electric field. But the particles themselves come from the vacuum. They are vacuum fluctuations made real by the intense field. The electric field required for this is enormous. The critical field strength is about 10 to the 18th volts per meter, which is far beyond anything we can currently achieve in the laboratory. But there are proposals for testing the Schwinger effect using the next generation of ultra-intense laser facilities. The European XFEL, the Extreme Light Infrastructure Project in Europe, and similar facilities may eventually reach the field strengths needed to observe vacuum pair production. If they do, it will be a spectacular confirmation of our understanding of the quantum vacuum and its energy. Related to the Schwinger effect is the phenomenon of vacuum birefringence, which is another way that the quantum vacuum reveals its non-empty nature. Birefringence is a property of certain crystals, like calcite, which split a beam of light into two beams with different polarizations. Remarkably, the quantum vacuum, in the presence of a strong magnetic field, is predicted to behave in a similar way. The vacuum fluctuations, the virtual electron-positron pairs, interact with the magnetic field and cause the vacuum to have different refractive indices for different polarizations of light. The vacuum becomes, in effect, an anisotropic crystal. This effect was predicted by Heisenberg and Euler in 1936, very early in the history of quantum electrodynamics. For decades, it was too tiny to measure. But in 2017, a team of astronomers using the Very Large Telescope in Chile reported the first observational evidence of vacuum birefringence. They observed light from a neutron star called RxJ 1856.5-3754, which has an incredibly strong magnetic field, about 1 billion times stronger than the strongest fields achievable in laboratories. The polarization of the light from this neutron star showed signatures consistent with vacuum birefringence. While the result is not yet conclusive and more observations are needed, it is a tantalizing hint that the quantum vacuum really does have optical properties, that empty space really does behave like a crystal when immersed in a sufficiently strong magnetic field. These are phenomena that most people have never heard of. Vacuum birefringence, the Schwinger effect, the dynamical Casimir effect. They sound like science fiction, but they are real predictions of well-established physics, and some of them have been confirmed experimentally. They all tell the same story. The vacuum is not empty. It is a rich, complex, dynamic medium with physical properties that can be measured and manipulated. And this story has implications that go far beyond fundamental physics. It has implications for technology, specifically for the most revolutionary technology of our time, quantum computing. Quantum computers operate at temperatures very close to absolute zero, typically around 10 to 15 millikelvin, far colder than outer space. They need these extreme temperatures to protect the delicate quantum states of their qubits from thermal noise. But even at these temperatures, zero-point fluctuations remain. They cannot be eliminated. And for superconducting qubits, which are essentially quantum harmonic oscillators, zero-point fluctuations are not just background noise. They are fundamental to how the qubits work. A superconducting qubit is a tiny electrical circuit that behaves as a quantum system. At its lowest energy level, it still exhibits zero-point motion, the irreducible quantum jiggling of the electrical current in the circuit. The qubit's quantum behavior, its ability to exist in superpositions of states, to be entangled with other qubits, to perform quantum computations, is intimately tied to these zero-point fluctuations. Understanding and controlling zero-point energy is not just an academic exercise. It is essential for building the quantum computers that may revolutionize everything from drug discovery to cryptography to artificial intelligence. In fact, the entire field of circuit quantum electrodynamics, or circuit QED, which is one of the leading approaches to quantum computing, is essentially the study of how to engineer and control the quantum vacuum fluctuations of electromagnetic fields in superconducting circuits. Researchers in this field designed circuits that have specific vacuum fluctuation properties, tailored zero-point energies that enable them to create and manipulate quantum states with extraordinary precision. It is zero-point energy, harnessed and controlled, that makes quantum computing possible. So zero-point energy is not just a theoretical curiosity. It is a technological enabler. The quantum revolution in computing, sensing, and communication is built on the foundation of vacuum fluctuations. Now, I want to address something that I think is very important. Throughout this video, I have been telling you about the reality of zero-point energy, about its experimental confirmation, about its role in cosmology and technology. But there is another side to the zero-point energy story, a darker side. And that is the world of pseudoscience, scams, and fraud. Zero-point energy has been seized upon by charlatans, fraudsters, and well-meaning but misguided individuals as the basis for claims of free energy devices, perpetual motion machines, and over-unity engines. The internet is awash with videos and websites claiming to show working zero-point energy devices that produce more energy than they consume. These claims are, without exception, false. Let me be clear about this. There has never been a verified, independently confirmed, reproducible demonstration of a device that extracts net usable energy from the quantum vacuum. Not once. Not ever. Every single claim of a working zero-point energy device has either been debunked, found to be fraudulent, or failed to withstand independent scrutiny. The scams typically follow a pattern. Someone claims to have invented a device that taps into zero-point energy to produce unlimited free power. The device is demonstrated in a carefully controlled setting where independent verification is not possible. The inventor claims that the government or oil companies or the scientific establishment is suppressing the technology. Money is sought for further development or commercialization, and the device never materializes. These scams cause real harm. People invest their money, sometimes their life savings, in fraudulent schemes. Public trust in real science is eroded, and the legitimate scientific study of vacuum energy is tainted by association. So how do you distinguish real science from pseudoscience when it comes to zero-point energy? Here are some guidelines. Real scientific research on zero-point energy is published in peer-reviewed journals and scrutinized by other experts. It makes predictions that can be tested and potentially falsified. It is consistent with the established laws of physics, particularly the laws of thermodynamics. And it is transparent about its methods, data, and uncertainties. Pseudo-scientific claims about zero-point energy, on the other hand, typically bypass peer review. They rely on testimonials and demonstrations rather than reproducible experiments. They claim to violate or transcend the laws of thermodynamics. They invoke conspiracy theories to explain why the technology is not widely available, and they often seek investment rather than scientific scrutiny. The laws of thermodynamics are not optional. They are among the most tested, most confirmed, most fundamental laws in all of physics. The second law of thermodynamics, which says that the total entropy of a closed system can never decrease, has been verified in every experiment ever performed. No device has ever been demonstrated to violate it. And any claim of a free energy device is, by definition, a claim to violate the second law. Extraordinary claims require extraordinary evidence, and no extraordinary evidence has ever been presented for any free energy device. This does not mean that zero-point energy research is not worth doing. It absolutely is. The Casimir effect, the dynamical Casimir effect, vacuum birefringence, the Schwinger effect, and many other phenomena are real, important, and worthy of study. The cosmological constant problem is one of the deepest unsolved questions in physics. Understanding the vacuum is essential for quantum computing, particle physics, and cosmology. There is a vast amount of legitimate, exciting, important science to be done. But it must be done rigorously, honestly, and within the framework of established physics. If you have followed this video all the way to this point, you deserve a round of applause. You are clearly someone with a deep intellectual curiosity and a genuine love of understanding. If you are still here, do something for me. Write quantum mind in the comments so I know how many people made it this far. And if you have not yet subscribed, this is your moment. Click that subscribe button and turn on notifications. The kind of deep, thorough, no shortcut science content you've been watching in this video is what this channel is all about. Every video is a journey, and I want you to be on every one of them. Now, let me take you to what I think is the most profound aspect of this entire topic. We have covered the science. We have covered the experiments. We have covered the technology and the controversies. But there is a deeper level, a philosophical level, a level that touches on the very nature of reality and existence. The story of zero-point energy tells us something extraordinary about the universe. It tells us that nothing is not nothing. True emptiness does not exist. The void is not void. Wherever you look, at whatever scale, from the subatomic to the cosmic, there is something rather than nothing. Energy, fluctuations, activity, life in the most fundamental physical sense. This challenges our deepest intuitions about reality. We naturally think of the universe as consisting of things and the spaces between them. Matter here, emptiness there. Stars here, void there. But quantum physics tells us this distinction is illusory. The space between the things is just as full, just as energetic, just as real as the things themselves. There is no background stage on which the play of the universe unfolds. The stage itself is part of the play. The vacuum is a player, not a spectator. This idea connects to a vision of reality that John Archibald Wheeler, whom I mentioned earlier, articulated with characteristic eloquence. Wheeler proposed what he called the participatory universe, the idea that the universe is not a machine running according to predetermined rules observed from outside by passive spectators. Instead, the universe is a participatory phenomenon in which the act of observation, the act of inquiry, plays a role in shaping reality. Wheeler summarized this vision with a phrase that has become famous: it from bit. Everything, he said, every particle, every field, every force derives its existence from the answers to yes or no questions, from the information that constitutes the universe. The universe is not made of stuff. It is made of information, and zero-point energy is deeply connected to this vision. The vacuum fluctuations are, in a sense, the universe asking questions of itself. The uncertainty principle says that you cannot know everything about a system simultaneously, that there is an irreducible fuzziness, an irreducible information gap at the heart of reality. And zero-point energy is the physical manifestation of this information gap. It is the energy of uncertainty itself. This is not mysticism, it is physics, but it's physics that touches on questions that were traditionally the domain of philosophy and religion. Why is there something rather than nothing? What is the fundamental nature of reality? Is the universe made of matter or energy or information? These are questions that humans have been asking for thousands of years, and zero-point energy brings us closer to answering them than ever before. Let me now connect all of this to the future, because the story of zero-point energy is not just about what we know. It is about what we do not know, and what we do not know may be the most important part. The biggest unsolved problem related to zero-point energy is the cosmological constant problem, which we discussed earlier. The fact that our best theoretical prediction of the vacuum energy is wrong by a factor of 10 to the 120 tells us that something fundamental is missing from our understanding. This is not a minor discrepancy. This is a gaping chasm in our knowledge, a screaming signal that our current theories are incomplete. Solving the cosmological constant problem will almost certainly require a revolution in physics comparable to the quantum revolution of the early 20th century. It will require a theory that unifies quantum mechanics and general relativity, a theory of quantum gravity. And the leading candidates for this theory, string theory and loop quantum gravity, both have profound things to say about the vacuum and its energy. In string theory, which proposes that the fundamental constituents of the universe are tiny vibrating strings rather than point particles, the vacuum is an extraordinarily complex entity. The theory predicts a vast landscape of possible vacua, estimated at roughly 10 to the 500 different possible configurations. Each configuration corresponds to a different possible universe, with different physical constants, different particles, different forces. The vacuum energy, the cosmological constant, takes a different value in each configuration. Our universe corresponds to one particular vacuum, one particular point in this vast landscape, with a cosmological constant that happens to have the tiny value we observe. Within this framework, the cosmological constant problem is reframed as a selection problem. Why did the universe end up in this particular vacuum and not one of the 10 to the 500 others? In loop quantum gravity, which proposes that space-time itself is quantized, made of discrete atoms of volume and area at the Planck scale, the vacuum has a very different character. Space-time is not continuous but discrete, a network of tiny loops and nodes. The zero-point energy of this quantized space-time is naturally finite because there are no modes with wavelengths smaller than the Planck length. This could potentially solve the infinity problem in the vacuum energy calculation, though the details are still being worked out. Both of these approaches are still under development, and neither has been experimentally confirmed. But both offer the tantalizing possibility of resolving the cosmological constant problem and achieving a deeper understanding of zero-point energy and the vacuum. There are also experimental frontiers that may shed light on these questions. The next generation of cosmological observations from satellites and ground-based telescopes will measure the properties of dark energy with unprecedented precision. If dark energy is not a simple cosmological constant, but varies in time or space, this will provide crucial clues about the nature of vacuum energy. Gravitational wave observatories like LIGO, Virgo, and the planned space-based observatory LISA may detect signatures of quantum gravity effects in the gravitational wave background, effects that are related to the quantum fluctuations of space-time, the quantum foam that zero-point energy drives. The future of this field is incredibly exciting. We are on the brink of a new era in our understanding of the vacuum, of space, of energy, and of reality itself. And the key to all of it, the thread that connects everything, is zero-point energy. Let me now bring together everything we have discussed in this video. We have covered an enormous amount of ground. We started with a simple question: is space really empty? And the answer resoundingly is no. Space is not empty. It never was. It never can be. We learned that the ancient Greeks debated the nature of the void, and that Aristotle's conviction that nature abhors a vacuum dominated thought for 2 millennia. We saw how Torricelli and Pascal created the first artificial vacuums, and how the concept of the ether was invented to fill the supposed emptiness of space, only to be disproven by the Michelson-Morley experiment. We saw how Einstein's special relativity appeared to confirm that space could be truly empty, and then how quantum mechanics, developed by Planck, Heisenberg, Schrödinger, and others, revealed that it could not. We understood Heisenberg's uncertainty principle and how it guarantees that no system can ever have zero energy. We saw how this leads to zero-point energy, the irreducible ground state energy of every quantum system. We extended this to quantum field theory, where every field at every point in space has zero-point fluctuations, making the vacuum a seething ocean of quantum activity. We explored the experimental proofs. The Casimir effect, where 2 metal plates in a vacuum are pushed together by the pressure of vacuum fluctuations, first predicted in 1948 and confirmed with increasing precision from 1997 onward. The Lamb shift, where vacuum fluctuations shift the energy levels of hydrogen, confirmed to extraordinary precision. The anomalous magnetic moment of the electron, the most accurate prediction in all of science, a direct consequence of the electron's interaction with the quantum vacuum. We asked whether zero-point energy can be harvested for practical use. We saw that the mainstream view, supported by thermodynamics, says no, because zero-point energy is the ground state and you cannot go lower. But we also explored the loopholes. The Casimir effect, which does extract energy but cannot provide net free energy. The dynamical Casimir effect, where accelerating boundaries create real photons from the vacuum. Stochastic electrodynamics, which offers an alternative perspective on the vacuum, and the interest of organizations like NASA and DARPA in exploring these possibilities. We connected zero-point energy to the biggest phenomena in the cosmos, dark energy, the mysterious force accelerating the expansion of the universe, which may be vacuum energy. The cosmological constant problem, the 10 to the 120 discrepancy between predicted and observed vacuum energy, the worst prediction in all of physics. Quantum foam, John Wheeler's vision of space-time as a turbulent, fluctuating entity at the Planck scale. The Unruh effect, which shows that the vacuum is observer-dependent. Hawking radiation, where vacuum fluctuations at black hole horizons cause black holes to evaporate. We explored the role of zero-point energy in the birth of the universe, how the vacuum energy of the inflating field drove cosmic inflation, how quantum vacuum fluctuations during inflation became the seeds of all cosmic structure, how the galaxies, stars, planets, and we ourselves are children of the quantum vacuum. We discussed the possibility that the universe itself emerged from nothing, from a quantum fluctuation. We looked at cutting-edge phenomena, the Schwinger effect, vacuum breakdown in intense electric fields, vacuum birefringence, the optical properties of the quantum vacuum, the role of zero-point energy in quantum computing and technology. We addressed the pseudoscience and scams that surround zero-point energy, and we discussed how to distinguish real science from fraud. And we explored the philosophical implications, the idea that true nothingness does not exist, that the void is not void, that the vacuum is a dynamic, creative, energetic entity, that the universe may be made not of stuff, but of information, that the energy of uncertainty, the energy of the ground state, the energy of nothing, is the foundation of everything. This is the story of zero-point energy, and it is, I believe, one of the most beautiful, profound, and inspiring stories in all of science. But the story is not over. In many ways, it has barely begun. The cosmological constant problem remains unsolved. The nature of dark energy remains mysterious. Quantum gravity remains elusive. The question of whether zero-point energy can be harnessed remains open. The deepest questions about the nature of the vacuum, of space, of reality, of existence remain unanswered. And this is what makes science so extraordinary. It is not a finished body of knowledge. It is a living, evolving, ever-deepening adventure of discovery. Every answer raises new questions. Every mystery solved reveals deeper mysteries. Every horizon reached reveals horizons beyond. If this video has changed the way you see reality, if it has given you a sense of wonder about the universe, if it has made you think about the space around you differently, then please do 3 things. First, hit the like button. This video took an enormous amount of research and effort to create, and your like tells the algorithm that this kind of deep, thoughtful content is valuable. Second, subscribe and turn on notifications. This channel is dedicated to exploring the deepest mysteries of the universe, and I have so many more journeys planned for us. The third, share this video with someone you care about. Knowledge is the one thing that multiplies when you share it. Send it to a friend, a family member, a classmate, a colleague, anyone who has ever looked up at the night sky and wondered what it all means. And leave a comment. Tell me what you want to explore next. Should we dive into dark matter? Should we explore the nature of time? Should we investigate parallel universes? Should we ask whether the universe is a simulation? The possibilities are endless, and I want this channel to be driven by your curiosity. Now, I have taken you through the main body of our journey, but I am not done yet, because there are several more fascinating aspects of zero-point energy that deserve attention, and I want to make sure we leave no stone unturned. I want this to be the most thorough, most comprehensive, most complete exploration of zero-point energy that you have ever encountered. So let us go even deeper. Let us explore some of the more subtle, more nuanced aspects of this topic that are often overlooked. One such aspect is the role of zero-point energy in the stability of matter itself. Have you ever wondered why atoms are stable? Why don't the electrons spiral into the nucleus? In classical physics, they should. A charged particle moving in a circle as electrons orbit the nucleus should radiate electromagnetic energy and lose speed, spiraling inward until it crashes into the nucleus. This was one of the great puzzles of early 20th century physics, and it was one of the motivations for quantum mechanics. The quantum mechanical answer is that the electron in an atom occupies a ground state, a lowest energy level, below which it cannot go. The uncertainty principle plays a direct role here. If the electron were to spiral into the nucleus, its position would be very precisely known, confined to a tiny region near the nucleus center. But by the uncertainty principle, this would mean its momentum would become very uncertain, very large. The kinetic energy associated with this large momentum would exceed the energy saved by being close to the nucleus, So there is a minimum orbital size, a ground state, that balances the electrostatic attraction of the nucleus against the quantum mechanical kinetic energy of the electron. And this ground state has 0-point energy. The electron in the ground state is not at rest. It is moving, vibrating, jiggling with 0-point motion. It is this 0-point motion that prevents the electron from collapsing into the nucleus. In other words, atoms are stable because of 0-point energy. The very existence of solid matter, of chemistry, of biology, of life itself, depends on the 0-point energy of electrons in atoms. Without it, all atoms would collapse. All matter would cease to exist, and the universe would be a soup of nuclear particles with no structure, no complexity, no life. 0-point energy is not just a curiosity. It is the foundation of all material existence.